today's forecast didn't call for rain, snow, or hail, but bouncy balls. You step outside for a stroll. The sky feels weird. Suddenly, every cloud unloads teaspoon-sized rubber balls, each about 2.7 centimeters wide. Cute, right? Think again. Let's bounce into what would happen if it really rained bouncy balls for a whole day. At first, it would appear as if some sort of scientific experiment has gone wrong. To understand how strange this could get, we could start by looking at what a typical heavy rainstorm usually brings. On average, it releases about 0.76 centimeters of water per hour, or 7.6 millimeters per hour, according to meteorological standards. Over the course of the next 24 hours, that would add up to about 18.2 centimeters of rainfall, or 182 liters of water per square meter. Now, imagine if that same volume were made up of small rubber spheres instead of water. Using the volume formula for a sphere, each 2.7 centimeter diameter ball, or radius of 1.35 centimeters, has a volume of 10.3 cubic centimeters. To match 182,000 cubic centimeters of water, or 182 liters, you would need 17,670 balls per square meter. Multiply that by 1 square kilometer, or 1 million meters squared, and you would get 17.7 billion bouncy balls per square kilometer. Now, scale that to the Earth's surface area, and that would be nearly 9 quintillion bouncy balls. But hold on, it doesn't rain over the entire surface of the Earth at once. Most of the planet is dry at any given time. According to NASA and climate data, only around 10 to 15% of the Earth's surface is experiencing rainfall at any one moment. Let's use a high-end estimate. 15% of 510 million square kilometers is 76.5 million square kilometers. So, realistically, on any given day, rain might fall over about 76.5 million square kilometers. Multiply that by our bouncy ball density. That's still 1.3 quintillion rubber spheres bouncing across every rainforest, city, mountain, and street caught in the storm. But before we cover the whole planet, let's start small. Say, New York. New York covers about 780 square kilometers, or 780 million square meters. A full day of bouncy ball rain would drop around 13.8 trillion bouncy balls on the Big Apple. But New York doesn't get storms every day. On average, it rains about 121 days a year, with roughly 10.4 millimeters of rain per rainy day. That's equivalent to about 1,010 balls per square meter, or around 788 billion bouncy balls on a typical wet day in just New York City. At first, they might bounce gently on the streets and sidewalks, but these aren't toys dropped from a shelf. They would fall from high up in the sky. As they drop, the balls would pick up speed. Most of them would hit the ground at speeds between 50 and 70 kilometers per hour. Now, imagine that kind of impact happening billions of times every minute. Windows could crack, rooftops might dent, and small objects might get knocked into the air. And this would only be the beginning, because these balls wouldn't stay put. They would bounce, repeatedly. Most rubber balls have a coefficient of restitution, COR, around 0.8, and this implies that every bounce retains about 64% of its energy. Therefore, unlike rain, which quickly drains away, these rubber balls would keep moving, rebounding off buildings, people, and each other. Streets would become difficult to use. Sidewalks would feel unstable. Cars might struggle to keep traction, and the longer it goes on, the more these balls would accumulate with nowhere to drain. Eventually, this would lead to something far more dangerous. Within minutes of the bouncy ball rain starting, videos would flood social media with people posting clips of rubber spheres bouncing off rooftops, piling up on roads, and smacking into windshields. At first, it might seem comical, like a real-life cartoon coming to life, but that feeling wouldn't last. Accidents would start happening fast. A delivery rider knocked off his scooter, a pedestrian hit by falling balls from 10 stories up. The mood would shift from curiosity to concern. In some places, the military might step in, not to fight, but to organize mass evacuations from high-density zones. This wouldn't just be a strange storm. It would become a full-scale societal breakdown, all thanks to synthetic rubber and gravity. Nature wouldn't be spared either. Birds might collide mid-air. Forests could become unstable, and aquatic ecosystems would definitely suffer. In lakes and rivers, balls would float or sink, disrupting aquatic ecosystems. Fish and smaller species might mistake the rubber for food, especially microfauna. And since most bouncy balls are made from synthetic rubber, they wouldn't break down easily. The damage could last for years. The rubber storm would hit the farms hard. Crops could get flattened, soil compressed, and irrigation systems blocked. With so much damage, farmers might lose a big part of their harvest, and that means food prices would hike up like crazy. But the economic problems wouldn't stop there. Power lines could fall, roads would become unusable, and railways might shut down. Insurance claims would pile up, and in large cities, cleanup costs could reach hundreds of billions. Eventually, the storm would stop, and the skies might clear up, but the aftermath would be overwhelming. Cities that experienced the downpour would sit buried under approximately half a meter of rubber spheres. Drains would remain clogged, power lines damaged, and millions of bouncy balls stuck in every corner of urban infrastructure. With a bit over a quintillion balls scattered across the planet, the question would be, how do we clean this up? Burning the rubber would release harmful chemicals. Burying them would only delay the problem. Recycling that many synthetic balls? Nearly impossible. And cleanup workers, they would face an incredibly difficult job ahead of them. So, what if it had rained bouncy balls for a day? It might begin with amazement, quickly spiraling into chaos and leaving behind a world buried in synthetic spheres, logistical problems, and ecological downfall. But more than anything, it would remind us just how fragile our systems really are when faced with the absurd physics of the unexpected. So next time you see clouds gathering, maybe it's best to hope that it's just rain.